All right, so you tried the practice problem. Here's our kind of walkthrough of it in case something went wrong. You can kind of figure out what went wrong and figure it out. So if you have this trouble light and it gave it a weight, W, of 5.6 newtons. This is our mg value of 5.6 newtons. They did put a W on there, so I put W on there as well, but you could also call it mg. So they want us to find the tension in A, B, and C. And so the first step you're going to want to do is you're going to want to just kind of isolate the weight and say, well, what forces are acting on that trouble light? Well, gravity's pulling it down with 5.6 newtons, and tension C is pulling it up. And I note that that trouble light is not accelerating, and so since it's not accelerating, the sum of the forces is 0. Up forces are added, down forces we subtract, and so then we find out that the tension in the cable is equal to the weight, which is 5.6 newtons. Now we need to go over and solve for tension A and B. This step over here, you can typically do just by looking at it. If there's only one string supporting it, it's going to equal its weight. Now, when we come over here, one thing we'll tend to do is we'll consider that this string is actually part of that trouble light. And so instead of having this intermediary tension C, we'll just kind of draw it like this, where those two strings are pulling up, A and B, and this weight is pulling down and tension C just doesn't exist. Otherwise, what you would have is you just have A, B, and then you could have tension C down as well. But typically we just ignore tension C because it cancels out, because it's pulling up here and pulling down there, and we can smoosh those two together and tension C will disappear. All right, now for this one, it's not just a one-dimensional situation. There's forces in both the X and Y directions. So that means we're going to have to add up the forces in the X direction and add up the forces in the Y direction. So the first thing you need to decide, is it a first law or a second law problem? This is a first law problem because it's not accelerating. Therefore, we know that these are 0. It's not accelerating the X or the Y. Next, what you had to do was you had to resolve these tensions into components. Okay? Remember to use SOHCAHTOA, so if it's adjacent to my angle, and you'll note that I took the angle that was up here and I moved it to down here. I just prefer to have my angle next to where my vector starts. It just makes a little more sense in my head. So these angles are the same. In this case, because it's 45, you could have also done this side of your triangle. Over here, here's our 30. If you use this side of the triangle, then it would have been 60. So make sure you used the correct angle, whichever side of that triangle you were on. I like to always go from the horizontal, just what I like to do. So here we have TB cosine of 45 is along the horizontal, and then I have TB sine of 45 here. Then we have TA cosine of 30, TA sine of 30. If you would like, you could have redrawn that picture, something like this with your sines. So this was our TB sine 45, TB cosine 45. We had our W, which was 5.6, TA sine 30, and TA cosine 30. It's nice to redraw that because it's a little easier to see which forces are in the X direction and which forces are in that Y direction. Okay, now we need to add up those forces in the X direction for our X equation, add up the force in the Y direction for our Y equation. So in the X direction, I have TB cosine 45 minus TA cosine 30. And in the Y direction, the ups are TA sine 30 plus TB here, TB sine 45 minus that weight down. At this point, you have a system of equations to solve. A little bit further down on this page, I'm going to teach you how to put it into a matrix and solve it that way. But first, I'm going to show you how to solve it algebraically. Okay. So if I have two equations with two unknowns, I'm going to solve one equation for one unknown in terms of the other, and then I'll substitute in. So in this example, I'm going to go ahead and solve for TA first. So I have TB cosine of 45 equals TA cosine 30, and then I'll just divide that cosine 30 over. So I have TA is equal to TB cosine 45, all divided by the cosine of 30. What I can do now is I can substitute all of that in for TA here, and now I'll have an equation over there that only has TB in it. Okay. So I have TB cosine of 45 divided by the cosine of 30. So that's all I've substituted in for that TA. There's still that sine 30 there. Sometimes people forget to include that sine 30 plus TB sine 45. And I'll move that W, or that 5.6, to the other side. What we can do now is we can factor out a TB out of each of those terms. So we have TB times this mess. All right, so I have cosine of 45, but then there's a little tricky tiger trail there. We got sine over cosine. Sine over cosine makes tangent, so I get the tangent of 30 plus sine 45 equals that. Wait, I'll even put my 5.6 in now. Now to finish solving this for TB, I just need to divide all this stuff in parentheses over to the other side. And so TB is going to be 5.6 divided by cosine 45 times the tangent of 30 plus the sine of 45. Making sure when I type this in my calculator, I do put parentheses around that stuff. All right, type that in your calculator. You get 5.6 divided by that. You should end up with 5 newtons. Once I know my TB, I can plug that TB in over here. So TA is equal to 5 times the cosine of 45 divided by the cosine of 30. And you should end up with a value of 4.1 newtons. A good rule for you is the more vertical the string, the more of that weight it's supporting. So in overall, it will be the larger of the two tensions. So since TB is more vertical, it has 5 newtons, and TA is a little less vertical, it's smaller than that 5 Newton number. So there you go.